Space-time circuit Hamiltonian constructions and applications.
Okay. So I decided to give a whiteboard talk. I hope that will be successful. And so what I'll talk about is a different construction for mapping a quantum circuit onto a Hamiltonian. And using this construction to prove to get some QMA results. Now, yesterday we heard that sort of QMA completeness results are, no longer fashionable. So, so this is, maybe too late to come with these results. But I think what my interest in this is to understand this construction, which is related to some papers that were written in 2001 by Mizell et al. And to then, for example, apply it to QMA. But I also believe there may be other applications of this constructions that may, who knows, may help us with PCP theorem or so. We don't know. So I think it's worthwhile to at least understand in what sense this construction is different. So, let's start with a little bit of introduction. And the problem is, of course, that most of you know these things quite well, but some don't. So I have to decide to what level of detail I'm going. So it was already alluded to yesterday. There's a standard construction due to Feynman to map a quantum circuit onto a Hamiltonian. What Feynman imagined is that instead of running a quantum circuit with, turning Hamiltonians off and on, you'd have one master Hamiltonian that runs the whole computation. And then Kitaev used this construction to prove certain QMA, get QMA completeness results. So first, just review this construction very, very briefly. So we have a circuit, quantum circuit, where we have just n qubits and gates U1 to UL. And in this Feynman-Kitaev construction, the Hamiltonian will act on those n qubits, but it will also act on a clock. And so we define a new register, a clock, T, and T runs from 0 to L. And this space-time construction will be different in that instead of defining one global clock, we'll define a clock for every qubit in the circuit. So that is where this will be different. We'll see the consequence of that. So then what the Hamiltonian does is this. So just let me write it down. This is the gate that should be happening at time t. Minus u. This is just your Hermitian conjugate.
You get a
darker. Yeah, the problem is I looked at whether it was the black. There's no other black, so I try it with blue. It's also not. Is that better? Yeah. Should I rewrite? I just say sometimes I write down an equation, but I try to also capture it in words, so we don't. It's always a challenge of a whiteboard talk. Okay, so then what the Hamiltonian does is say this term is not so important, just to use to make it positive semi-definite. But it's very simply what the Hamiltonian does. It moves time forward from t minus 1 to t, and then a gate ut is applied on the qubits to which it should be applied. And because this term by itself is not Hermitian, one has to add its Hermitian conjugate. And so we also have dynamics by which time runs backwards, and the gate the gate action is undone. Yeah? And so that's one term in the Hamiltonian. That's the term that corresponds to the gate ut. Yeah? So there will be one term for every gate, and then the circuit Hamiltonian is just a sum over from t is 1 to L of ht. And the important property of this this Hamiltonian is that it has a unique ground state, and if everybody can see it here, because I just want to keep this thing up to compare, it's the history state, which is let me write it down. For oxide. So it's not unique. Okay, so it's not unique in the sense that we can put an input state in this history state. So it's an eigenstate with zero energy of the Hamiltonian for every psi. But once we fix psi, it's unique. And it captures the whole history of the circuit, right? If we were to measure a specific time, t, we were to find the output of the circuit at that time. Yeah?
So t goes from 0 from 1.
T goes from 0.
But then your 0 is not defined, right?
Yeah, but then it's just the initial state. Yes, that's true. It's not defined, but indeed, in that case, you have to.
So
Yeah.
the time is a cyclic also.
Not in this way. We can also make time cyclic, yeah. In this case, time is just running on a 1D line from 0 to L. And so, having this history state, you can read out the output of the computation. Like I said, by measuring t with probability 1 over L, you find the final time. But if you pad the circuit with some identity gates, so you're not forced to find a single time, but you're forced to find, you can find any time in some, some output interval, then you can make the probability for getting that output to a constant. I know this is standard for some people who already know this. And you can use this also, so there's another use of this construction for adiabatic computation, by which you say, well, I like to be in the ground state. In order to simulate a quantum computation, I like to be in the ground state of the circuit Hamiltonian. But now, initially, I'm in some trivial state. Say I interpolate the circuit Hamiltonian with this trivial Hamiltonian with ground state I can prepare. I gradually turn off the trivial Hamiltonian and I turn on the circuit Hamiltonian. Then you can prove that you can get to this history state, and then you can read off the output of the computation. And lastly, I said this is also the crucial element in QMA completeness proofs. And we haven't seen anything, we have probably have referred to QMA, but so I just want to sketch not the details, but of what is the connection with QMA and the circuit Hamiltonian. Once I've done that, I can start talking about how we modify this. Okay? Okay, so the thing is, so for QMA completeness, we have to look at, so what are the problems in QMA, which is quantum NP? So these are promise problems. So it's a promise problem that we specify by some sets L yes and L no, which are non-intersecting, and such a class of problems is in QMA if the following holds. If the answer to the problem is yes, then exists a witness, a quantum state, such that a quantum circuit, let me just write it down. A quantum circuit Cn, which takes the instance, the x, as input, and the witness outputs 1 with high probability 1 minus epsilon. And if x is an L no, for all witnesses, the probability that this is 1 is less than epsilon. And we can make this very, very small. And this witness, so the circuit, this verification circuit, is some polynomial time circuit in N, and this witness is also some polynomial, has some polynomial number of qubits. Pn, and N is the length of x. So in order to prove that the problem is QMA, yes?
I just wanted to make sure I'm understanding this problem. So if there is some small level probability that it cannot decide the existence?
It makes a small error.
Yeah.
Yes. Yeah. That is inherent in complexity classes associated with quantum computation, that you allow for a small error.
Well, I don't necessarily mean that it says yes when the answer is no. I'm saying that it's possible that it returns neither yes nor no.
Yes, that's because it's a promise problem. Yes. Yeah. Yeah. Yeah, and you'll see that also when we prove QMA completeness of problems, there's also a promise. And so we prove that determining the eigenvalue of a Hamiltonian is either, the eigenvalues, there's an eigenvalue less than a certain value A or larger than B. and there's a gap between those. Right? So there's a promise inherent to that. So, so in order to prove that problems are QMA complete, we have to relate any such problem in QMA to another problem, which is this problem of determining the lowest eigenvalue of a Hamiltonian. So what one does is that one constructs for any L and instances, one constructs the following. If x in L yes, then we have a Hamiltonian H of x, such that the minimum eigenvalue of h of x is larger than a. Smaller than a. Smaller than a. And so if the answer is no, then that Hamiltonian, which depends on x, of course, is has an eigenvalue. All eigenvalues are larger than b, and this is some separation. There's some, and these cannot be exponentially close together. So this problem by itself, if you have a Hamiltonian or class of Hamiltonians to decide whether this is true or that is true, it's a problem in QMA. But one can also show that you can relate any problem in QMA to this problem. So if you're able to solve this problem, you can solve any problem in QMA. But in order to execute this, you have to map these problems and instances thereof onto a Hamiltonian, right? And what do we do? What do we have about what we know about these problems is only that there exists this verification. If x is in the lang, or if x is in L yes, there exists a verification circuit that takes x and the witness, and with high probability the output's 1. So that fact we want to translate into the existence of a Hamiltonian that has this low eigenvalue. So for that we need to represent the circuit and its action as a Hamiltonian, and that's where the construction there comes in. Okay, so now that was just a sketch how this goes, and many people I think here know the ins and outs of this construction, so I don't want to dwell on it. So what is now the overview of what I'm going to do? First, I'm going to discuss this new space-time circuit, the Hamiltonian construction, and say some more, make some general comments about it, and apply it to one-dimensional quantum circuits. And the reason we apply it to one-dimensional nearest neighbor quantum circuit is because that's the only case we can actually analyze so far. Then I will discuss the relation with the fermionic model, which was introduced by Mizell and all in 2001, and then I'll come back to how we put things together for QMA. Okay, so like I already announced, the difference between the new construction and this one is that every qubit will have its own clock. Yeah, so if instead of defining one register T, we'll define, we'll call this the ST construction. So we're going to define a register, a multi-time register, T1 to Tn. They're n qubits, so everybody has their own clock. And furthermore, this circuit, which is the verification circuit in the QMA case, but let's take a general circuit. Its circuit will have some depth d, and also some size s, and the number of gates. And one reason I found this construction interesting is that this way of mapping a circuit onto a Hamiltonian allows one to capture the geometric structure of the circuit. Unlike the Kitaev construction where you just say, well, this is gate 1 to L, and we just have a clock that runs from 0 to L, and we lose all the information in the circuit that is of interest to people studying physics, for example, because circuits with low depth which are geometrically local are of interest to people who study, as ansatz for ground states of Hamiltonians and so on. And so one can apply this construction to a one-dimensional circuit, as I will do, or 2D, or a mirror, and so on. And the circuit Hamiltonian will inherit properties of that quantum circuit. Okay, so these times now, because the circuit has depth d, these times will just run from 0 to d. Yeah? And so now we have to specify what are the terms in the circuit Hamiltonian, like this. And so there may be 1 qubit gates and there are 2 qubit gates. Now I will focus on 2 qubit gates because we always need them. Let me just say, well, for 1 qubit gate you have, it's very simply, for 1 qubit gate, let's say this is a 1 qubit gate, this term, this clock update, is only the clock of that 1 qubit, obviously. Other clocks do not change their time. For a 2 qubit gate, I have something different and I'll write it down explicitly. So let's say I have a 2 qubit gate that acts in the original circuit at some time t, with t is somewhere in this depth, between qubits p and q. And now it's some term which applies the unitary on those 2 qubits. And it minus Hermitian conjugate. Let's just write down the last t plus t minus 1. And so now what we say is, if both qubits have time t minus 1, we both update their times. And the Hermitian conjugate, which is just the time reverse. And we have these 2 terms again to make it positive semi-definite. It actually plays a role in the spectral analysis. It would be simpler if we didn't have these terms. But, okay, so there are other issues with that. And one thing I want to note is that we're going to be interested in the ground state of this Hamiltonian. And it's clear that if the clocks of these 2 qubits are not synchronized, that this energy of this has 0 energy. Yeah? And so this is something you can worry about. That when that there are potentially many more 0 energy states, because it's much easier for clocks to get synchronized. So in that, in this larger space of clocks, I have to structure this a little bit. Because there is a space, let's imagine that I start with all qubits synchronized. Yeah? And let's imagine I have the circuit that only applies 2 qubit gates. Yeah? So 1 qubit, 2 qubit gate is applied, those 2 qubits move forward in time. Another qubit gate is applied, and you see that clocks do not stay absolutely synchronized. They vary slightly. But what does remain true is that if both qubits have clocks that are before the gate, you never run into a configuration when one clock of a qubit is after the gate and the other clock is before the gate, right? If I start with the all synchronized configuration. So I'm going to define something I call proper configurations. And the reason I'm defining is that because the circuit Hamiltonian, so the circuit Hamiltonian is the sum. It's the sum of these terms. The circuit Hamiltonian preserves a subspace of these time configurations.
Yeah. Apply an identity gate if there's no gate applied to a qubit at a particular time?
This depends on what you model. So yeah, you could say, I'm going to fill the circuit everywhere maybe there's no gate apply. I'm just going to pretend there is an identity gate and I move that clock forward.
Okay.
Yeah, because...
It's not necessary for your construction?
No, so in my construction, so in the way we use it for QMA, we look at a circuit, which maybe I'll draw it here. It's just a circuit with qubits, 1, 2 to n. And there are 2 qubit gates throughout. So this is 3, 4, and then I'm standing here in the wrong way. Is this clear?
Yeah.
So everywhere throughout the circuit there are 2 qubit gates. And that's what I'm going to apply it to. Yes? And that makes, I want it to be as symmetric and sort of simple as possible.
What's your range of T?
T is goes from 0 to D, which D is the depth of the circuit.
But that's for TI. So your T.
Every clock runs from 0 to D.
T goes to X.
Sorry?
He
T?
means other T.
Oh, this T. Oh, this also runs from 0 to D, because this is the, the thing is that in the original circuit, I just, write it like this, and I have these times, and the depth of the circuit here, so this runs also from 0 to D,
But only
but I have
So
to
you
specify.
for even T's.
What?
For even T's, right? I mean, you don't.
No, T just move even. No.
You haven't summoned P the Q in Q. That's what's
Oh, I
missing still.
Yeah, that's B.
Sorry, but say.
You have to summon P and Q. That's what's missing.
Oh, this is just a single term corresponding to a single gate. It's not corresponding to a whole layer at time t. Yes? Oh, but this is maybe. Oh, yeah. Sorry, this is the thing. Thank you. Yeah, it has to be summed over. The times, the depth layer that you're at, and the qubits that you act on at that layer here. Okay.
And there's no real geometry, so you're not requiring qubits to be neighbors or anything.
Well, I am in my analysis, yes.
Okay.
But one could expand. You could analyze this for many more general circuits. But and I would be happy if people can do the spectral analysis for this. So in the QMA completeness, you need to lower bound the gap of the Hamiltonian, and that's what we did for this model. And I think that's not so simple for general circuits. So I'll come to that problem.
Right.
But maybe people have good ideas. There's a lot of. I'm not saying it's impossible. It's just that we started with something simple because it's universal for quantum computation, and it turned out this is very nice to do this spectral analysis. Okay, so now we define. So the 2 types of time configurations. One which I call improper and one I call proper. And so this is the definition of improper T1, Tn. I can write it down explicitly if, promise it's a little bit, maybe I should say it in words.
So sorry.
Yes, sorry.
So here, it's not just a permutation. It's nearest neighbors.
Yes. So this is a circuit where the qubits are sitting on a line,
Yeah.
and they just interact with nearest neighbors. And one time step is with this guy, the other one is with the other guy. And I'm actually also assuming periodic boundary conditions in space.
And you wouldn't. Okay, so you wouldn't imagine that that's the worst case for mixing.
What was the question?
Whether it's the worst case for.
Whether it's the worst.
I don't know. We can talk about this. So the thing, maybe we can come back to this question, yeah? Okay, so improper times are the times basically such that there exists, in this sequence of times, there exists times such that one time of a qubit is after the gate and the other one is before. Yeah? So should I write this down? If at least of one pair of qubits, Q and P, which interact at time t in the original circuit, and go lower and lower, it holds that TQ is less than T and, let's say an and, TP is larger or equal to T, or TP is less than T and t cube is larger than t. And so in this case, the time of qubit q is before t, and the other one is after the time, and this one is the opposite case. And so the point is that if I start with an all synchronized time, all the qubit times are the same, when clocks are synchronized, my circuit Hamiltonian will never map beyond to these states. It preserves the space of proper time configurations. Yeah, and I will now label, so there are the proper time configurations. And I'll label them by vector t. Sometimes I'm also just saying that like t, just to make things a little easier. So what we want to do in QMA, we want to put a penalty, because we don't want to have zero energy configurations which have nothing to do with what the circuit does for our QMA, right? Because we have to look at the eigenstates of H and construct, argue that this is the case. So zero energy configurations are bad. And of course, it's very easy to create zero energy configurations that are improper. Just make all qubits unsynchronous. So we put a penalty to the Hamiltonian, which we call H causal, show this at the end, to penalize these configurations, and we can do that. Yeah? So let's now restrict ourselves to the space of proper time configurations.
You can do that exactly?
Yes, but and it's a term that commutes with the Hamiltonian, so it's and it's local also. Yeah. So we restrict to the proper time subspace, but there you can also ask, are there zero energy configurations that have nothing to do with the Hamiltonian? And it's not so easy. So let's just take an example, because they almost exist. And I'll give you an example. Okay, so here is a circuit. So in general, for more general circuits, they will exist. Now I'm going to try to construct. Now this is a qubit that goes in here, and these are its possible times. Yeah. So I can construct a configuration where this qubit has this time, and I want to make the qubits as synchronized as possible, but still being proper. Yeah. And so I can say, well, I can put this qubit over here, and this qubit over there. And of course I could continue this, go on forever. These are, we call this sort of light configurations, because they're in between the proper time configurations, which are more space-like. There's no causal relations between those, between the states of the qubits for those configurations, and the improper ones for which there are light-like correlations. Okay, anyhow, so this type of configuration here picks up no energy, because every time qubits are asynchronized, but they're still proper. No? But of course, this circuit has to terminate somewhere. So at some point, I have to go around the block and say, I'd stop this line over here. And here the qubits are synchronized, which means that the circuit Hamiltonian can move this forward. Now again, I could I could move this one up there. But of course, if I were taking out this gate, I just take out that term in the Hamiltonian, then there's no energy picked up here. So I can generate zero energy proper configurations for certain circuits, of course. So I have to be a bit careful with this. And so if I have periodic boundary conditions in space here, I have to also make sure that, this comes back to this. So I make these configurations, they look kind of like, yeah?
I mean, like, if you didn't put a hole in your circuit, then
It would not be a problem.
right.
Yes, right. If I just include, so I can avoid them pretty easily if I just include gates throughout and things propagate. And so in that case, these proper time configurations for this circuit they're like a string, because, you know, if you fix the time of one qubit, it has to be proper. There's only two places that the other qubit time can be, either there or there. Yeah? So it has a string, and what the circuit Hamiltonian does, it lets this string, you know, vibrate, right? This moves forward and becomes like this thing, etc., and it can move backward. And that's how that dynamics exactly, you know, but we'll see that later if we re-represent these strings in a slightly different way. So I'm going to restrict myself to circuits which have 2 qubit gates throughout with this structure, so I avoid any 0 proper time configurations. Okay, so in that case, I can also, there's one more comment I want to make about this, is that there's a nice general thing you can say about the circuit Hamiltonian in this space of proper time configurations, because it's actually the Laplacian of a graph. You can associate a graph with it. It's not so surprising. So let's, so we can associate a graph with it, where the vertices are the proper time configurations, and there exists an edge if T, H circuit, T prime, is unequal to 0, and it, you know, in general what it will be equal to, it will be some unitary gate. It's some unitary gate that relates the time t prime to the time t. And so what you can do, and this is actually similar what you do with this in this Feynman-Kitaev construction, you have your circuit Hamiltonian which depends on these unitaries, but you know, you don't really care what they are. And you could do a unitary transformation if you restrict yourself to the proper time space, such that these are absent, and such that you get, so there's the circuit Hamiltonian, there's some unitary transformation. Actually, well, maybe I should write it this way. So, circuit Hamiltonian. Restricted to the proper time space, P proper, I can do a unitary transformation that maps this onto the Laplacian of a graph, T prime, T prime. And this Laplacian is the degree matrix minus the adjacency matrix. So, and the degree matrix comes from the diagonal terms. They are of this type. There are contributions from that. They come with the positive side. And the adjacency matrix comes from the negative terms. In the Kitaev construction, you know, this is just the identity. You're only, you know, spectrum of this is the same as the spectrum of the Laplacian. But in this case, the degree matrix is not a regular graph. Why not? Because if I have a very synchronized configuration, there are many more states that I can go to, many more vertices in its neighborhood, than a very unsynchronized configuration. Right? Like one of those where I just have something like this. Right? I can only, this configuration, only these parts can actually move, they can vibrate. Whereas if it's like this, I can have little bumps, you know, I can go to new proper time configurations by those steps. Okay, so
Sorry, so
Yeah.
so now, okay, so you're getting almost a random walk on a line back, except that the line is of length.
well, I'm getting a string, right? The string,
Yeah.
it's just a diffusion of
Yeah.
a string.
No, I know, but
Yeah?
since only the ends can move, don't you effectively get a random walk on a line, except the line is now length d, and then it's the string stretches out for s, so you have d over.
Which are getting the way I formalize it, but maybe you have another insight, is that you have this string, and it's the motion of the string.
Yeah, no,
So I pick a
understand.
boundary point, And that has a 1D random walk.
Yeah.
And then there are internal motions of the string. There's the deviation from this boundary point. Let's say I have, we'll come to that more maybe explicitly. And the rest of the string can be characterized as deviations of this point. And there's motion, there's dynamics in that. So I decouple the dynamics in terms of a forward motion of this boundary point, which is chosen arbitrarily, and then the vibrations of the string.
Right. No, I
Yes, but
guess
that's
the
not
issue
really-
is the mixing time D or S.
The mixing time is really, there is an n, if you say what is the gap here, it really goes like n squared.
N is the total number of gates.
N is the length of the string, and D is the form.
Yeah.
And that is really, I think, what we see also. Is we have a first excited state, which is a good ansatz, and which has energy of this order, which is not quite an eigenstate, but the.
Right, but that's really coming about because of this.
But the problem is that, but I think that so there's, what I'm trying to think about also is that, we get a promise gap here, and I like a promise gap that just depends on D. Because the internal motion of the string doesn't really matter for, this boundary point is like, where this boundary point is determines where the output qubit. And the internal vibrations of the string actually don't really matter for this. But I mean,
yeah, but it's the 1D structure of it. If you were doing this on a hypercube,
yeah,
you should get better.
Well, so what it would be, the thing is that, of course, if it's on an expander, if it is for an expander circuit, that every, you just put random 2-qubit gates in, there would be much more slack in this string, right? Because I interact with 1 qubit now, and much later I interact with that qubit again. Means that my clocks and that qubit clock can be highly synchronized. And, okay, so the question is, what does that do? I think it makes the space of proper time configurations larger. I don't know what it actually does with the gap. So the thing,
Log n.
what, sorry?
No, it will be actually small. It can be smaller because of the expansion.
Yeah, you can have them this.
All of them will
log
be
n.
more synchronized. We'll have
No,
to-
they would not be synchronized. No, this is the more synchronized. This is the most you can synchronize it, because the more the less frequently these qubits interact, the more slack the string have to deviate.
No, see, if you were in a hypercube, certainly you would get, you'd have degree log n. But then instead of getting these long, these long light cones where you're basically moving only from the endpoint, you would now have, you would actually be interacting with, you'd keep the string more taut, because right now there's nothing to synchronize parts of the string that are far away.
No, that's true. Yeah, it only gets synchronized by moving the outer parts in.
Yeah.
That's true. Yeah. But yeah, maybe we could. Yeah.
So I just have a follow-up.
But yeah.
So if you take the circuit to have the property that all the 2-qubit gates go through the first qubit, then the internal configurations really are just like a hypercube. If you consider the possible positions of every other qubit, there's 2 choices and there should be 3. So then it really is a hypercube tensor with a line. And
But that's the case you analyze, is that right?
yeah, that's
But the gap there is.
the gap there is, again, determined by the gap of the line. Yeah, so in the silver sorry, in the gates. Because now the depth is equal to this.
Okay, well,
Yeah, but I'm not sure what, maybe we should talk about that later. I'm not sure what the exact one is.
Yeah.
okay. So, there's one technicality which I do not like to discuss too much, but the way we're going to do the spectral analysis of the circuit Hamiltonian is made much easier if we assume that the circuit Hamiltonian has periodic boundary conditions in time. And one can also, if you have the standard RWTH construction, where you just have some circuit which doesn't have periodic boundary condition in time, you can map it onto a circuit Hamiltonian which this time runs in a circle. So there is a time 0 and here's a time L, and the circuit Hamiltonian from these time steps, it does, these all do the gate, and then there are also terms that do, move the time forward by which you start undoing the gate. So if you were moving over here to there, you have undone the last gate. And of course this unitary evolution to this point is the same as the unitary evolution to that point. And so this needs to be, you can't put arbitrary gates here, otherwise you have a condition on this input space. So you can do that, and you can also do that in this construction. And you have to modify the definition of what it means to be improper, but the intuition is the same. So we will assume that the circuit Hamiltonian is something where this sort of string is on a torus. Because first of all, there were periodic boundary conditions in space. That was this circuit. And then furthermore, there are periodic boundary conditions in time. And so I have some torus, and there is a string that is around it, which is diffusing. And I have to look at the gap of that. Okay, so how we're doing on time? 20 minutes?
20 minutes.
Oh, okay. Yeah. Okay, so now, yeah, but maybe I should also say what people want to hear. We have two. So, do people want to know a little bit about how this connects with the fermionic model? No takers. Okay, so let's just do that briefly. So there is a model that was introduced by Mizel, of which claims were made how it was useful for adiabatic computation, and these claims were not proved very rigorously, and that was part of the motivation for this work.
Do they claim things for just the one-dimensional circuit, or do they assume a different geometry?
It's very hard to just extract what they claim, because they seem to claim something for more general, but it just can't be. So I think they wanted to focus on one-dimensional circuits, because that's what their original proposal was with hopping fermions and so on. But they're also they're also possibility of having single qubit gates, and possibly there's no constraint like there have to be 2 qubit gates everywhere, as far as I know. So.
So if your circuit was 1D local, then this Hamiltonian is also 1D local.
Yes, this Hamiltonian is also the clocks, of course, are not. Clock is just. I haven't talked about any clock realization. Yeah, but that's not what comes in this fermionic thing, because in the fermionic. Okay, so in this, their model can be stated in terms of fermions, but it's just a model of hopping particles. Yeah? So let's say you have a circuit like that, and for every qubit Q, you introduce kind of a double track. And on this double track, there's a hopping particle. And the top track is sort of the state 0, and the bottom track is the state 1 of that qubit. So if this particle were to hop all over there, it would just stay in the state 1 for the whole computation. If you were doing single qubit gates on this particle, there would be some interactions. Let's say you start that would say, okay, I have a unitary gate with some amplitude, the particle goes there, with some amplitude the particle goes there. Yeah? So that's a unitary gate. But in all cases, this particle, it hops and it changes its internal state. And its internal state is then represented by whether it's on the top or the bottom track. And so if you have, if you want to now do 2 qubit gates, you want to have these particles hop together. Yeah? So they both hop forward or both hop backward, assuming that they're both somewhere. Let's say they're all here. And then they hop forward at the same time. but they also can do some. You can do a control NOT gate, so depending on whether this particle is on this track here or not, and this particle moves there. So that's basically the model. And what is important is that there is only one particle per track. And you can unitarily, if you put down that constraint, you can unitarily, reformulate that Hamiltonian in terms of a circuit Hamiltonian where the clock register is realized by what's called a pulse clock, where this is the length, so this track is of length d, so here's sort of d positions, and so this is a register of length d, this is the depth of the circuit, and when it's t, this particle or this clock is here. So that is a local, and this model, this fermionic model, is local in 2 dimensions, because it involves particle, it actually in terms of fermions, it's just quartic interactions at most, which involve fermions on one track hopping forward, or fermions on 2 tracks hopping forward. Yeah? So it's a 2-dimensional local quartic Hamiltonian. And I'm not going to sketch any detail, but you can relate it to our model. But this then realizes a certain clock, and we wanted to sort of analyze it, look at it a little bit more generally. Okay, so now let's come to the sort of how this is applied to QMA and what I need to do with my circuit Hamiltonian.
Sorry,
Yeah.
the spectrogram.
The spectrogram.
Getting to the spectrogram.
Yes, yeah, I can also skip some of the, okay. Yeah, I don't want to. Okay, so maybe I should say something about that. How we analyze the spectrogram. Okay. So we're going to skip the other parts of the QMA proof. And we need to analyze the circuit Hamiltonian. And a priori it looks, well, we're stuck on this for a long time because this is the Laplacian of a graph and it's fairly, intricate. It's not regular graph, although it has a lot of structure, of course. And then we did an important relabeling of these times that allowed for some better analysis. So I'm drawing this because I'm going to represent the times of qubits on the edges. Okay? So the times are on edges. The plaquettes, there are gates, 2-qubit gates. So if I look here, let's say I have a time here and a time there, and this gate happens, then these 2 times are moved forward to this. Yeah? That's the action of the circuit Hamiltonian. And the proper times I can represent like this. For example, I'm just drawing an arbitrary line, and it has to close here.
So are you drawing the graph?
No, the graph is high dimensional, right? It's on the space of these states. So every vertex in the graph is a string like this. But this string is much more easily represented in a different way, and I'm getting to that. So this string
So
is.
there's some significance to the fact that you rotated it by 45 degrees.
No, I mean it's just convenient visualization. There's not any. I think there's not.
And so, but time is now going.
No, time is still here. This is a sequence of. This is a space here, and this is the time. So I have times of qubits is a line.
It's just the alternation between odd and even now is clear.
I mean, I had the gate was something like this before, right?
Yeah.
And now it's just I think it's just a nicer representation of the circuit. I could have written the original circuit this way.
Sure.
Yeah, and so the thing is that what the gate does, it flips. You could say this is a domain wall of some, of a boundary of some membrane, right? And this is all the gates that have been done, and that's the boundary of them, of course. Yeah? And so we can present, and then if you look at this, and then you say, well, of course, I can represent such a string as pick a point like this, and then look at deviations from this point. And I call the deviation in this direction 1, I call that 0. So this is 0, 1. So here I have an n-bit string of deviations, and I have this point. And that captures the whole string. Right? So this t1 to tn is equivalent to a variable tau. And this tau goes from, these points, right? Tau, well, there are some transformations that happen with the circular time, but it turns out that tau is in zd. And x is an n-bit string of deviations. And so, that's just a related...
With constant weight.
Yes, with weight, because n over 2. Yes, because it has to close. Okay. So now I can just represent the circuit Hamiltonian is different base. So just check matrix elements by matrix element, what does it look like? And it's simple because you notice that, I can pick this arbitrary point, this point arbitrary, that these deviations do not act on this tau variable, right? I can have this, so for example, I have a move which is 1, 0 to 0, 1, so basically I have moves like 1, 0 back to 0, 1. And that's the type of terms that I should have in my Hamiltonian, which are like a sigma I plus sigma I plus 1 minus Cauchy-Riemann conjugate. And because these things and this should stay the same. Okay, because if I have a piece of the string, let's say this were flat here, then this doesn't move. No? So these things should be the same. So I'm just writing piece by piece, I'm just writing the action of my circuit Hamiltonian, this new basis. And what I get is something where there is, okay, so one comment you need to make is that this variable, if there is a term which maps this thing on that's doing this gate. That moves this variable forward, and it does that. So that's where the coupling is, right? So there's one place here where this n-bit string, the motion of it, is coupled. Yeah? But otherwise it's decoupled. So, yes, so now I want to, so I can write down what so the problem is now, so okay, so this, I need to see how I do this. I'm going to write down an eigenstate. So it turns out, let me just give you the sort of mathematical. I'm going to define the state is a plane wave state. It's a superposition over all these tau with some momentum vector k. And it turns out that the circuit Hamiltonian, with some tilde because I represent it in the new basis now, that this is, these are eigenstates of the Hamiltonian in the following way. So these are eigenstates, and for every vector, every k, I have a Hamiltonian hk. And this Hamiltonian hk now only acts on these deviation variables. And this Hamiltonian hk is just a Heisenberg model. So, let me see.
I'm sorry.
I don't know whether we have to...
So what you're interested in is the random walk of that, this wiggly
Yes,
line,
yeah.
of depth d and width
Yes.
n. And so, is it a classical analysis of that? Or?
I looked, and there are some, one paper I saw. I mean, I tried to apply these techniques, there's conduction, conductance bounds and all that. And let's see, I didn't see how to do that. But there is also recent work they call the random walks and random walks, because this is doing a random walk and this is also a random walk.
Yeah.
And they did an analysis, but they did it very similar as what I did, sort of a decoupling. But I haven't looked at all the details.
But eventually, somehow the bound ends up being as though you were doing a random walk on a line which was n times d.
Well, I mean, the gap is,
Yeah,
yes,
yeah,
the
yeah. And
sentence
so-
of the gap, yeah.
Yeah, and there's no way of sort of reducing it, or you don't.
No, but the thing is, there are some things. But I could come to the end. Is that I believe there are, in the QMA results, you have this, you have the circuit Hamiltonian and its ground state, and then the gap, and then there is the in and the output thing. Yeah. But I believe there are excited states of this Hamiltonian that also violate this, cannot be null, zero eigenvectors of the input and output part. Why? Because I can just have all vibrations of this string. If I only care, this is the output qubit. Yeah? I can allow for many vibrations of this, and those states would still, have non-zero energy with respect to the input and output constraint, as long as this point has some overlap with the final state. So it's like I can take subspaces of states, not just the ground state. As long as there is sufficient support on the input, this string has to have, it's linear combination, sufficient support on the input qubits that are set to 0 and the output. And then I should be able to lower bound the energy there.
So I want to understand this point. So in Kitar's construction, you basically look at the random walk on one line.
Yeah.
You take the spectral gap, and then you use the geometrical lemma to show that the lowest eigenvalue is high.
Yeah.
Here you're saying maybe we can do the analysis classically for this random walk, but then the extra step that you're doing, that in Kitar's construction is something simple geometrically, here you have to be more careful because
No, it's not careful. I just see that in that lemma, one part, only this angle between subspaces only depends on D, doesn't depend on N. The only place where N happens is in the gap of the circuit Hamiltonian. But this is a very pessimistic estimate. I think there are states above the gap that are also would not lead to zero energy of the whole thing. I think this gap is actually higher, therefore.
Okay.
And this gap may just scale. The question is whether this gap actually scales with D instead of N. Now, of course, for 1D circuits, this is not interesting, because D, in order to do universal computation, D has to be. But if I take an expander circuit and it scales with D, then then it may be of interest. So I think that this gap estimate is potentially too pessimistic, because and I don't know, with the regular construction you have this, this state, the ground state is this uniform superposition over all tau. And you can say, well, can I allow any excited states, that a linear combination of the ground state and excited state, low-lying, would also, be not null states for this H in plus H out. Right? But that's harder to do because there's much less room, because, if you can create a localized state at a certain time, that will definitely have zero energy for the input and output constraints, because it has, yeah. Sorry, it just goes a bit off track. But okay, so the thing is that this HK turns out to be a Heisenberg model, and maybe I have to indeed finish up, I think. Okay, so let me just write it down and write down the result. Okay, so HK is Zi plus 1 plus something I call delta K plus a half. This is probably okay, so the point is that I mapped this model onto a model that's been studied in physics and elsewhere. So if I just forget about this term, this is a very simple Heisenberg model, and its gap is known. It can also be related to Markov chains. but it also being treated with a beta ansatz, there is a condition that sum over zi is 0. Yeah, it comes out, and but I have a boundary term because here at this point I couple to these plane waves with k, so that the k dependence comes out in this term. So this is called a Heisenberg model with a partially twisted boundary. And so I have another, just some mathematical results that lower bound the gap of these Hamiltonians. So we know that for k is 0, we are in the ground state. And then we want to know what is the minimum eigenvalue of hk for any non-zero k. And one can prove that also using a Kitaev lemma. And the result, see, the thing is that the result is something you very much expect, and it takes a lot of work to actually derive that. Or d squared. Well, it's not. So it goes like this. It's something where the lowest eigenvalue of the circuit Hamilton goes like something of 1 over n squared times d squared plus some higher order terms.
Sorry, Bob.
Yeah.
So can you sort of say at a high level
Why?
what makes it work? So so the technique is not canonical paths or coupling or so on, but what is the technique? So
Well, I think I have looked at Markov chains with an internal degree of freedom. I don't know, maybe that is of use. I think this case, it's this decoupling, that did the work. And
it's decoupling meaning.
well, decoupling in terms of this variable, which has very simple dynamics, which I can write the eigenstates, and then I have a Hamiltonian in one dimension, which is a lot simpler. But that, of course, is not a good answer, because I cannot apply this technique the same way on two-dimensional circuits. So it's something that just happens for this circuit. But there may be... But I don't know. I've tried also many other things, right? This is actually, maybe I'm just not, and this even bounding this was also not, you had to do some other tricks, but I don't know, it's not, of course we knew that this was the case already a long time before. This is what you expect. Maybe there's a much simpler way to derive this, I don't know.
Is it that different for a two circuit? It seems, there's one more that you mentioned, and it seems that you have a similar phenomenon where you have one line and then...
Yes, well, you have a boundary, right? So you can say, I have a boundary, and then I have deviations from this boundary.
Yeah.
Right? Because even one... Yeah, and this boundary moves forward, but I think it does get more complicated. The boundary now is like, a string. And so that...
Yeah, which itself you could attach to...
Which you could use this thing.
Which you could use that thing, right, exactly. I thought, but the problem is that it's not that parameterization, it depends on details that this happens to work. So it doesn't generalize, although it's clear that you can also write it as some point and deviations thereof, right? But just that the models you get kind of, I think is not so obvious. Although I think, well, maybe you can, because it's clear that you get some model with a higher spin degree of freedom on this thing, because you have more, if you have a 2D circuit, you don't interact every other time step with the other qubits, potentially, like maybe 4, so you get a... Okay, so let's, yeah.
Further questions? Or do you want to see?
No, people can read the paper if they're wanting to more technical details.
Further questions? Or yeah.
So how does this state, which is not zero eigenstate, you suspect does not disturb your computation too much, look like? Is it like torn up membrane?
Well, okay, so let me say this. So I have these, well, you have to understand there is these Hamiltonians. And for every one of those Hamiltonians, this variable is in, this fixed state. And let's assume that variable is really, where the output qubit is. Yeah? So if I fix my k, I fix this state, yeah, then I can never create a state that has no support on this final time. It will always have some support there through this counter variable. Yeah? So I fix so I say I'm looking only at the state H of 0. Now you can ask, can I take linear combinations of the states in the space H0? What are those states? They are states for which this counter variable is in this uniform superposition of all times. And this can be in any state. Yeah? Now, if I can create states in this space that have no support on the beginning of the circuit, then it's bad, right? Because then I can buy. So I should want to restrict myself to the subspace where I always have some support also on the beginning. But it seems like if I'm in those space, assuming that, I'm not sure those are low-lying states, but if I'm in that space, at least I know that I would have to pick up an energy penalty from H in plus H out.
And then the gap you would expect from that subspace to be like constant, or just 1 over n instead of 1 over n squared?
Well, the problem is that I don't know I don't know enough about this. The thing is, because there is also HK prime, and the gap, if the lowest eigenstate of here is 1 over n squared d squared, then I may already be in trouble, right? Because if I'm not allowed to take. So I don't know. I may have to,
Okay, so I guess. Please.
So the title says that there are applications. So are these computer science applications or these fermionic?
No, so we proved the QMA completeness of a two-dimensional, spatially local model, which can be realized by quartic fermionic interactions under there is some constraint. But this is, there have been results in two-dimensional fermionic models like that, but they are, they use, the terms in the Hamiltonian that are increasing with system size, like results by Schuch and Verstraeten. But I have to say that I think the application to QMA is somewhat weak in the sense that it's not giving you, it's not giving you improvements directly, I find, over what we have proved before, like QMA completeness of one of the Hamiltonians on a line or something. But if we just want to demonstrate you can use it for QMA completeness, and it has different features that may come into other uses in complexity theory, and also for adiabatic computation. Does that answer your question?
Yes.
Okay, so let's thank Barbara.